Welcome back to QHSE Talks, where we approach safety the way it is meant to be practiced, technically grounded, regulation-driven, and professionally accountable. In today's episode, we are deep diving into Chapter 10 of David Yates' Safety Professionals Reference and Study Guide, a chapter that many people underestimate until they realize just how much competence it actually demands. The chapter's titled Noise and OSHA's Hearing Conservation Program, and it sits at the intersection of industrial hygiene, occupational health, and applied engineering. This chapter is not theoretical. It is explicitly anchored in OSHA Standard 29 CFR 1910.95, the regulation that governs how occupational noise must be evaluated, controlled, documented, and medically tracked. And what makes the standard especially critical is that it does not wait for damage to occur before it applies. It is designed to intervene early, before hearing loss becomes permanent. At the center of the standard is the Hearing Conservation Program, and the trigger is very precise. When employee exposure reaches or exceeds an 8-hour time-weighted average of 85 decibels A-weighted, equivalent to a 50% noise dose, the program is no longer optional. Monitoring, testing, training, and record-keeping all become mandatory. That immediately raises a technical question. How do you know when you've crossed that line? The chapter walks through the instrumentation required to answer that question correctly. Type 2 sound level meters as a minimum for compliance, octave band analyzers to break noise into frequency components so hearing protection can be selected intelligently, not generically, and personal noise dosimeters, worn by workers, integrating sound levels across the full range from 80 to 139 decibels over an entire shift. But measurement alone is not enough. Once employees are enrolled in the program, audiometric testing becomes a cornerstone. Baseline audiograms must be established within strict timeframes and under controlled conditions, including mandatory quiet periods. And those results are not just medical data, they are compliance data. Because when a standard threshold shift occurs, defined as an average 10 decibel or greater shift at 2,000, 3,000, and 4,000 hertz, that outcome has regulatory consequences. An established STS is not merely a trend, it is a recordable occupational injury. What makes this topic especially demanding is that noise is not managed by intuition, it is managed by math. OSHA's permissible exposure limits are based on a 5 decibel exchange rate, meaning every 5 decibel increase cuts allowable exposure time in half. Dosage calculations, TWA conversions, logarithmic decibel addition, and the inverse square law all come into play the moment more than one noise source exists, or the moment a worker moves within a space. And all of that technical complexity exists for one reason: the biology. Because ultimately, noise control is not about instruments or equations. It's about protecting a system in the human body that, once damaged, does not recover. The transition from conductive to sensory neural hearing loss is the line between temporary impact and permanent disability. And that line is crossed silently. Which is why this chapter, and this episode, demands a level of detail that cannot be compromised. And that's the perfect place to shift the conversation, because when you truly understand what's at stake, you understand why precision in this field is non-negotiable.
And that level of detail is, it's completely non-negotiable in this field. Noise hazards are persistently ranked among the top occupational concerns everywhere. This isn't just about, avoiding a citation. It's about preventing a permanent, life-altering injury. The thing about noise-induced hearing loss is that it's insidious, it's cumulative, and it's usually painless, which means you have to be proactive.
You can't wait for the symptoms to show up.
You can't. By then, it's too late. So mitigation requires really precise intervention based on scientific principles. To manage this effectively, a safety professional has to be, fluent in multiple disciplines. You have to understand the specific auditory anatomy, because where the damage is determines if it's permanent. You have to know the exact regulatory trigger points, and you absolutely must be adept at the acoustic engineering calculations. If you can't combine 4 different noise sources mathematically, you just can't accurately assess the risk in a room with multiple machines.
And that's the challenge we're embracing today. So we'll start with the human element, that subtle but devastating physiological damage. Then we'll move into the program itself, what the standard mandates. And finally, we will dedicate the rest of our time to breaking down the logarithmic structure of decibels and the key formulas. We're talking calculating total sound levels, measuring propagation, determining dose, and quantifying the effectiveness of controls. Okay, let's unpack this right at the source then, the physiological damage. Before we even talk about solutions or regulations, we have to grasp the magnitude of the problem. What is actually happening inside the ear when hazardous noise causes hearing loss, and how do we categorize it?
It's a great place to start. We categorize hearing loss fundamentally by the physical location of the damage within the auditory system. And this classification, it dictates everything. It tells you the prognosis is the loss reversible. And that, in turn, dictates how the condition has to be managed. Our sources detail 4 primary classifications based on location, plus a couple of others related to psychological or environmental factors. The first type is conductive hearing loss. This is purely mechanical in nature. It happens in the outer or middle ear.
Okay, so we're talking about the ear canal, the eardrum.
Exactly. The ear canal, the tympanic membrane, the eardrum, and those 3 tiny bones in the middle ear, the ossicles. Their whole job is to transmit sound vibrations efficiently. When you have conductive loss, it just means the sound waves aren't making it through that pathway efficiently to the inner ear.
So the sound waves are hitting some kind of physical or mechanical barrier, and that's diminishing the amplitude before it even gets to the core sensory organ.
Precisely. The key descriptor for conductive loss is that it's solely a loss of loudness. The sound is attenuated, it's quieter, but it's usually not distorted. And the causes, as the source material lays out, are generally pretty straightforward. Common causes are things like built-up earwax, cerumen blocking the canal,
Sure.
or a physical obstruction of the eustachian tube, often from an infection or fluid, or, more drastically, a perforated eardrum.
A perforated eardrum sounds much more serious. That's an acute physical injury, right? From trauma or a bad infection.
It is. But the good news here, if there is any good news in hearing loss, is that conductive loss often has a positive prognosis.
Meaning it can be fixed.
That's correct. From a medical standpoint, this loss is often reversible. You remove the earwax, clear the infection, or a small perforation heals and function can be restored. But, and this is important for safety professionals, even though it's often reversible, you still have to monitor it. It can compromise how well hearing protection works and just generally makes a worker more vulnerable. A perforated eardrum is a serious risk factor on a noisy job site.
Okay, so that's conductive loss. Mechanical, often reversible. What's next?
Now we get to the one where safety professionals have to focus almost all of their concern in an occupational setting. This is the second type. Sensorineural hearing loss. This type is what the entire hearing conservation program is designed to prevent, because the damage is, well, it's overwhelmingly irreversible.
And this is happening deeper inside the auditory system, right? In the inner ear. What's the critical structure being damaged here?
We're talking about the cochlea, which houses the organ of Corti. This tiny, incredibly complex structure is the true sensory part of the ear. It transduces the sound. Inside the organ of Corti are thousands of microscopic receptor cells, known as stereocilia. Most people just call them the hair cells.
Right.
These hair cells are responsible for translating the physical vibrational energy, which is just pressure waves, into electrical impulses that travel along the auditory nerve to the brain.
So when excessively loud noise comes in, it's generating so much kinetic energy that it's physically damaging or destroying those delicate hair cells.
Exactly. Imagine a field of grass. A gentle breeze, a normal sound, just makes it sway. But a powerful sonic shock wave, that's hazardous noise, can shear or destroy those blades of grass permanently.
And just like the grass in that field, those cells don't grow back.
They do not regenerate in humans, so damage here is permanent. This is the difference between a temporary inconvenience and a permanent disability. Furthermore, and this is a critical detail for anyone looking at audiogram results, damage from hazardous noise tends to happen first at the higher frequencies.
Why is that?
The hair cells that detect high-pitched sounds are located right at the base of the cochlea. They're the first ones to encounter the sound wave as it enters the inner ear, and they absorb the maximum energy.
Which explains why the classic sign of noise-induced hearing loss isn't just someone saying what all the time. It's difficulty distinguishing certain words or following a conversation in a noisy room. You lose that high-frequency clarity first.
Precisely. An employee might initially just think, oh, I just need people to speak up. But what's really happening is they're missing the sibilant sounds, the Fs and the sounds, which are all high-frequency parts of speech. This is often one of the very first indicators of permanent noise-induced damage, even if the overall volume of a conversation seems fine.
Okay, that's a huge distinction. What are the other classifications?
We can move through the rest pretty quickly. There's mixed hearing loss, which is just a combination of both the ones we discussed. Maybe an aging worker with existing sensorineural damage who also gets a bad ear infection, causing some temporary conductive loss.
A bit of both.
Right. And then you have two types that are generally outside the scope of a direct occupational noise injury. First is central nervous system, or CNS, hearing loss. This is damage in the neural pathways between the inner ear and the brain. The sources are very careful to point out this is often caused by factors that have nothing to do with noise, like a stroke or a tumor. And finally, there's psychogenic hearing loss. This originates in the mind, maybe from emotional trauma. The physical auditory system is totally intact, but the brain's perception of sound is altered. It's rare, but it has to be differentiated from physical damage.
That covers the types of damage based on location. Now let's shift to the sources or the causes. We need to be able to distinguish what an employer is responsible for versus, say, normal aging or lifestyle choices.
Yes, this is where we define the vectors of acquisition. We already mentioned obstruction and disease. The other three categories are all about exposure energy. First, you have acoustic trauma. This one is easy to identify. It's hearing loss from a sudden, overwhelming, intense noise.
Like an explosion.
Exactly. Think of a firecracker going off right next to your ear, a gunshot without hearing protection, or a catastrophic equipment failure that creates a huge blast. This can cause immediate profound damage, both conductive, like a ruptured eardrum, and severe sensorineural damage. Second, we have to differentiate between the background, long-term exposures, and here we have two key terms, presbycusis and sociocusis.
This differentiation feels absolutely vital, especially when you get into things like workers' compensation claims or just reviewing audiograms year to year. If a worker's hearing changes, the employer needs to know if they were the cause.
Indeed, presbycusis is the biological baseline. It's defined simply as hearing loss from the natural aging process. It's an expected progressive deterioration that happens to everyone regardless of their environment. It's gradual and generally predictable.
So that's the part you can't avoid.
Right. But then you have sociocusis. This is defined as hearing loss due to continuous non-occupational noise exposure. This is the damage we do to ourselves.
So listening to music too loud on headphones.
That's the big one today. But also attending loud concerts, using unsilenced power tools at home on the weekend, riding a noisy motorcycle. It's all the background environmental noise we subject ourselves to outside of work.
And the significance here is that when a safety professional looks at an employee's audiograms over time, they are trying to strip away the presbycusis, the age factor, and the sociocusis, the lifestyle factor, to isolate that final category. Noise-induced hearing loss. That's the specific damage caused by the occupational exposure that the regulations govern.
Precisely. The goal of the safety professional isn't to fix the damage from age or someone's personal stereo. It's to rigorously demonstrate that the workplace is not adding to that burden. If a significant threshold shift or STS occurs, and that's a very specific, defined change in hearing, the employer has to be able to show that it wasn't due to their working conditions. This ability to isolate the occupational component makes this distinction incredibly important.
Okay, now that we understand the irreversible states here, protecting those non-regenerative hair cells, let's shift to the regulatory framework. Here's where it gets really interesting, because the law dictates exactly who needs protection and how we have to measure and manage that risk. So what are the non-negotiable concrete elements of OSHA's hearing conservation program?
The anchor for the entire program is the standard 29 CFR 1910.95, the Occupational Noise Exposure Standard. This is the absolute governing document for noise control in general industry. It says all the action triggers and the mandated program elements. And the core mandate, it really revolves around two critical thresholds that determine who gets included in the program.
Yeah.
Any employee with an occupational noise exposure that equals or exceeds 85 dBA, that's decibels adjusted, or a noise dose of 50%, must be included in the hearing conservation program.
Let's pause on that 85 dBA number for a second. That is the action level. So if we measure an employee's average exposure at 85 or higher, even if their total accumulated risk over 8 hours is still acceptable, the alarm bells have to go off. Why is 85 the trigger when the actual legal limit for continuous exposure is 90 dBA?
That 5 dBA difference is the safety margin. OSHA recognizes that noise-induced hearing loss starts long before you hit the legal limit of 90. So the 85 dBA action level acts as a mandatory trigger. Hitting 85 dBA or a 50% dose means the employer has to immediately institute a full program. That's monitoring, audiometric testing, training, and making hearing protection available to everyone. It's the preventative gateway.
And the 90 dBA is the hard ceiling.
That's the permissible exposure limit, or PL. 90 dBA corresponds to a 100% dose. Once you cross that 90 dBA TWA, the situation becomes much more serious. You might be looking at mandatory engineering controls or even a citation if it's not addressed. The whole program is built to manage the risk at 85 so you never exceed 90.
So that 85 dBA action level is probably the most important administrative number in the whole program. It triggers a massive compliance effort.
It absolutely is. Now let's focus on one of the most logistically challenging but scientifically critical parts of that effort: audiometric testing. This is how we establish a baseline of someone's hearing and then track changes every year. And the source material highlights a hugely important and often frustrating requirement for employers.
What's that?
Employees require a minimum of 14 hours away from a noisy environment before their baseline or annual audiometric test.
14 hours?
14 hours. And this isn't just about making sure they show up refreshed. It's a scientific necessity to eliminate a temporary measurement error.
This rule is fascinating. It gets right to the heart of the physiological concern, doesn't it? We're dealing with what's called a temporary threshold shift, or TTS.
Exactly. When a worker is exposed to loud noise during a shift, those hair cells we talked about can get temporarily fatigued. They're stunned, but not permanently destroyed yet. This temporary loss of hearing sensitivity, the TTS can last for many hours. If you test that worker immediately after their shift, the audiogram will show their hearing as being worse than it actually is.
And if that artificially low reading is recorded as their baseline, then years later a real permanent loss might be completely masked. Or, on the other hand, if they recover a bit, their next test might wrongly show an improvement, which also masks a problem.
Precisely. The logistics of this 14-hour rule are immense. You can't just test everyone at 5 o'clock on a Tuesday. You have to ensure the employee has had enough time for full auditory recovery. This often means testing first thing in the morning before a shift starts, or requiring a specific schedule change that guarantees those 14 hours of quiet time, which can include time at home or sleeping. This dedication to accuracy just highlights the reality. We're measuring microscopic, permanent damage, and we have to filter out every temporary effect.
The level of precision required is staggering. So moving from the biology to the tools, what kind of precision is mandated for the actual measurement equipment?
We have to talk about the minimum acceptable measurement equipment. To accurately determine employee exposure levels, the standard requires, at a minimum, a Type 2 sound level meter.
And what does Type 2 mean?
Sound level meters are categorized by their precision. Type 1 meters are precision grade. You'd use them in a lab or for very sophisticated engineering work. Type 2 meters are considered general-purpose survey instruments.
But for OSHA compliance under 1910.95, the Type 2 is acceptable as long as it meets a really rigorous accuracy standard. It must have an acceptable accuracy tolerance of plus or minus 1 dB.
1 decibel. That's a tiny measurement on a logarithmic scale. A plus or minus 1 dB requirement seems incredibly strict for a general-purpose instrument. It is. And the practical implications are huge. It means calibration and maintenance are paramount. A 1 dB error could be the difference between measuring 84.5 dBA, where no program is required, and 85.5 dBA, where the action level is triggered, and a company might have to spend hundreds of thousands of dollars on a full HCP.
So the safety pro's job isn't just to hold the meter.
Not at all. Their responsibility is to ensure the meter itself is scientifically certified, calibrated regularly, and used according to strict protocols to maintain that critical plus or minus 1 dB tolerance. And the final cornerstone is just documentation and execution. The program demands meticulous records. You have to track who's in the program, the dates and content of their annual training, the schedule and results of their audiograms, and you have to prove that 14-hour rule was followed. And you need maintenance logs for your monitoring equipment. It's all built on a foundation of measured preventative action.
We've established the hazard, that irreversible hair cell damage, and the trigger point at 85 dBA. Now we hit the central technical challenge, quantifying sound. Because sound is an invisible energy hazard and our compliance thresholds are so specific, we have to rely completely on precise mathematical conversions. This is where we shift from biology into engineering and physics.
And we have to confront the nature of decibels right away. Decibels, or dB, are not a linear scale. They are a logarithmic scale. This is the single most important concept to get your head around in acoustics. Linear scales, like temperature or length, you can just add them up. 1 foot plus 1 foot is 2 feet. But logarithmic scales measure magnitude differences. They reflect these vast differences in the underlying physical energy.
It's like the Richter scale for earthquakes, right? A magnitude 7 isn't just a little bit stronger than a 6, it's 10 times stronger in terms of wave amplitude.
Exactly. The sound pressure level scale works in a similar way. If you double the acoustic energy, let's say you turn on a second identical machine, you do not double the decibel reading. Instead, you only increase the sound level by about 3 dB. This nonlinear reality means you can't just add noise levels, and it requires specific logarithmic formulas. If you tried to manage risk by adding 80 dB plus 80 dB and getting 160 dB, you fundamentally misunderstand the hazard.
So it's not intuitive at all.
Not at all. We're going to look at 2 primary calculation types that are absolutely indispensable for evaluating a hazard, combining multiple sound sources and calculating how that sound propagates over a distance.
Okay, let's start with the real-world scenario. You're in a machine shop. You've got a punch press at 95 dB, a blower at 90, and a couple conveyors running at 85 and 79 dB. How do we accurately calculate the overall total sound pressure level that an employee standing nearby is actually experiencing?
We use the total sound pressure level formula, which is written as L sub kit. The job of this formula is to temporarily undo the logarithmic nature of the decibel. We convert each individual decibel reading back into its linear energy equivalent. We sum those energies together, and then we convert that total sum back into the logarithmic decibel reading.
So you take it out of log scale, do regular math, and then put it back in.
That's the logic. The formula itself for total sound pressure level is expressed as L sub tet equals 10 times the log of, and then in parentheses, 10 to the power of L1 over 10 plus 10 to the power of L2 over 10, and so on for all your noise sources. Let's define the elements. L1, L2 up to Ln are just the individual sound levels in decibels. The real magic happens inside the parentheses with that 10 to the L over 10 function.
That's the part that converts it back to linear energy.
Exactly. It transforms the logarithmic decibel value back into a proportional measure of acoustic power. When we sum all those terms, we get the total acoustic power from all the machines combined. Then the final step, taking the log and multiplying by 10, converts that result back into the standard decibel scale we can measure.
The logic is brilliant. Convert some, convert back. Let's run the example from the source material, because I think the result is what really informs the control strategy.
Okay, so we have 4 noise levels running at the same time, 79 dB, 85 dB, 90 dB, and 95 dB. We plug these into the formula, transforming each one, so we get 10 log of, and then it's 10 to the 7.9 plus 10 to the 8.5 plus 10 to the 9.0 plus 10 to the 9.5. And if you look at the sheer magnitude of that last term, 10 to the 9.5, it's a huge number. It's completely dominating the sum. The others are orders of magnitude smaller. When you calculate the sum of those energy terms and then convert it back, the resulting total sound pressure level, the L sub Z, is approximately 96.59 dB.
Okay, that is the profound takeaway right there. The loudest single source was 95 dB. We had 3 other pretty noisy sources, including one at 9 dB, and the total noise level only went up by 1.59 dB. The 95 dB source is acoustically bullying everything else in the room.
Exactly. This calculation proves a fundamental principle of noise control. You gain almost no benefit by silencing a quiet machine if a much louder machine is still running. To make any significant dent in the total noise level, you have to focus your control efforts, enclosures, mufflers, whatever, on the absolute loudest source first. If you could knock that 95 dB source down by 10 dB, you would change the entire acoustic environment far more than if you just got rid of the 79 dB source entirely.
So that calculation tells us the noise level at the measurement point, but sound doesn't stay put, it propagates. If you measure a machine at 1 foot away, but the worker spends their whole shift 10 feet away, we need a way to accurately estimate how much that noise level drops over distance.
This is handled by applying the inverse square law to acoustics. The law basically states that for every doubling of distance from a point source, the sound intensity drops by a predictable amount. In acoustics, if we assume free field conditions, where sound radiates uniformly with no reflections, which is a bit of a theoretical ideal, the noise level drops by 6 dBs for every doubling of distance.
A 6 dB drop for every doubling of distance.
Right. And the formula for calculating the sound pressure level at a second distance incorporates this principle. It's dB sub 1 equals dB sub 0 plus 20 times the log of the ratio of d0 over dy. Let's clarify those 4 variables because they're crucial. dD0 is your original known sound level measurement, usually taken close to the source. dB1 is the new sound level you're trying to calculate at the second distance, like where the worker is.
And D0 and D1 are the distances.
Right. D0 is the original distance where the measurement was taken, and D1 is the second target distance where you want to know the sound level. They have to use consistent units, of course.
So let's run a quick example. If our dB0 is 100 dB measured at 1 meter away, so D0 is 1, and we want to know the level at 4 meters away, so D1 is 4.
Okay, so the ratio D0 over D1 is 1/4. You take 20 times the log of 1/4, which is approximately negative 12 dB. So your new level, dB1, is 100 plus negative 12, or 88 dB.
And that makes sense with the doubling rule. 1 meter to 2 meters is a 6 dB to drop. 2 meters to 4 meters is another 6 dB drop, for a total of 12.
Precisely. The mathematical relationship is reliable in ideal conditions.
But wait a minute. In a real factory with machines, steel beams, concrete floors, clutter everywhere, are free field conditions ever realistic? Aren't reflections and reverberation going to mess with this calculation?
That is the critical challenge, and it highlights the limitation of this formula. You are absolutely right. A typical industrial setting is highly reverberant. Sound bounces off everything. This means the actual drop-off is often much less than 6 dBs per doubling of distance. However, the formula is still indispensable. Well, first, it gives you a theoretical maximum drop-off, which is useful for a quick assessment. And second, if you are in a very large, high-ceilinged warehouse where reflections are minimal compared to the distance, it can provide a very close estimate. For safety professionals, this formula is crucial for defining boundaries and evaluating risk remotely. It lets you scientifically define a perimeter around a noisy machine, say a line painted on the floor at 8 feet where the sound level is calculated to drop below 85 dBA. That defines your hearing protection zone.
Okay, we've quantified sources and measured their propagation. Now let's move into the administrative and engineering metrics that actually govern compliance and evaluate our risk reduction efforts. We're moving into TW dose and calculations for engineering controls.
Right. TWA and dose are the ultimate regulatory metrics of accumulated risk. OSHA doesn't just care about how loud it is right now. They care about the total energy absorbed by an employee over a standard 8-hour shift.
So this links momentary loudness to total risk.
Exactly. The dose, which is a percentage, is the amount of the maximum permissible noise exposure a worker has incurred. A 100% dose corresponds to the 90 dBA PEL. A 50% dose corresponds to the 85 dBA action level. And the time-weighted average, or TWA, is the resulting dBA level that, if you were exposed to it continuously for 8 hours, would give you that specific dose.
So how do you calculate one from the other?
The standard formula for calculating the TWA from the daily dose is provided right in the source material, and it's tailored specifically to OSHA's required 5 dB exchange rate. The formula is TWA equals 16.61 times the log of D divided by 100 plus 90.
Let's talk about that structure. Why 16.61, why not 10, which we saw in the other log formula?
That 16.61 constant is what incorporates the crucial 5 dB exchange rate that OSHA requires.
And what is the exchange rate?
The 5 dB exchange rate means that for every 5 dB increase in the noise level, the permissible exposure time has to be cut in half. So if you can tolerate 8 hours at 90 dBA, you can only tolerate 4 hours at 95 dBA, 2 hours at 100 dBA, and so on. If OSHA used the standard physical definition of doubling acoustic energy, which is a 3 dB exchange rate, and many international standards use that, that constant would be 10. But OSHA's policy mandates the 5 dBA, which makes this TWA calculation specifically tailored for U.S. regulatory compliance.
That distinction 5 dB versus 3 dB, that feels like one of those classic details that separates basic knowledge from real technical expertise.
It absolutely does. It dictates how aggressive your controls have to be. Now let's just confirm the anchor points of the formula. If the dose, D is 100%, we plug that in. TWA equals 16.61 times the log of 100 over 100 plus 90.
The log of 1 is 0.
So the TWA is 0 plus 90, which is 90 dBA. The formula correctly links a 100% dose to the 90 dBA PL.
And at the action level.
If the dose is 50%, the TWA is 16.61 times the log of 50 over 100 plus 90. The log of 0.5 is about negative 0.301. Multiply that by 16.61, you get about -5. So the TWA is -5 plus 90, which equals 85 dBA.
So the formula confirms exactly what we said earlier. 85 dBA is the action level at 50% dose, and 90 dBA is the PL at 100% dose. This is the ultimate tool for converting a worker's daily noise monitoring data from their dosimeter into an enforceable 8-hour average.
Exactly. If that calculated TWA exceeds 90, the PL has been exceeded, and significant immediate action off in engineering controls is required. This calculation is the final, non-negotiable metric of accumulated risk.
Okay, so once we identify a hazard that needs controls, we have to prove those controls actually work. How do we mathematically evaluate the effectiveness of an engineered control, like a muffler on a ventilation system?
We use a noise reduction, or NR, calculation. The source material presents a calculation that's often used when you're evaluating enclosures or ductwork, where controlling airflow is intrinsically linked to noise reduction. This specific formula assesses effectiveness based on the volumetric ratio of air handling.
So it's about air movement.
Right. The provided formula for noise reduction evaluates the ratio between the volume of air needed to achieve a required throughput, like ventilation, divided by the physical volume of the room or the enclosure itself. So the formula is defined as NR equals the volume of air needed in CFM divided by the volume of the room in cubic feet.
Okay, so it's a ratio of air movement in cubic feet per minute to the static space volume in cubic feet. This has to be tied to the specific acoustic design of the enclosure then.
Exactly. The result gives us a reduction factor based on that ratio. Let's run the example from the source material to see how this works. The given data is the volume of air needed for ventilation is 319.06 CFM, and the room or enclosure volume is 113 cubic feet.
So you divide 319.06 by 113.
And you get an NR value of 2.82.
Okay, the number is 2.82. Now, I have to bring up the unit anomaly we saw in the source material here. The calculation gives you a ratio of CFM per cubic foot, but the source lists the final unit as dB per foot.
That's a good catch. That unit labeling is likely an error or maybe a simplification used in a specific instructional context. The calculation itself, though, the 2.82, represents the noise reduction factor achieved by that specific airflow design relative to the enclosure's volume. This factor is then used by acoustic engineers, often with tables or charts, to determine the actual reduction in decibels. This is a critical metric for engineers designing enclosures that have to maintain air quality or temperature while also being noise barriers.
Okay, so beyond mechanical controls and airflow, probably the most common engineering control in large spaces is acoustic treatment applying materials that absorb sound to walls and ceilings. How do we quantify the effectiveness of installing those absorbent materials?
We quantify this using the concept of sabins. A sabin is the standard unit of sound absorption. One sabin is equivalent to 1 square foot of a surface that provides 100% perfect sound absorption.
So concrete would have a very low sabin value.
Very low. A thick acoustic tile would have a very high value. We calculate the reduction based on the change in the total absorption units in the room before and after treatment.
And because we're talking about reducing energy, I'm guessing it's another logarithmic calculation?
It is. The formula for calculating the noise reduction in dB achieved by acoustic treatment is dB equals 10 times the log of A2 divided by A1. Let's define those variables. dB is the predicted noise reduction in decibels. That's what we want to find. A1 is the total number of absorption units, or sabins, in the room before treatment. This is the baseline acoustic character of the room.
And A2 is the total number of sabins after treatment. So it's A1 plus all the new absorption from the panels you installed.
Exactly.
This is a beautiful application of the log scale. So if we double the total absorption in the room, let's say we go from A1 equals 100 sabins to A2 equals 200 sabins, we plug that in. It's 10 times the log of 200 over 100.
Which is 10 log of 2.
Which is approximately 3 dB.
You nailed it. Doubling the absorption only gets you a 3 dB reduction. And this is a crucial lesson for anyone allocating resources. It's relatively easy to get the first few decibels of reduction by treating a very reflective, live room. But as you add more and more absorbent material, the cost-benefit ratio rapidly diminishes. You might have to double the surface area of your treatment just to get another 3 dB.
So this calculation gives the safety professional a concrete, scientifically justifiable return on investment. Instead of guessing, they can say, to drop our ambient noise from 87 dBA to 83, we need to increase our total room absorption from A1 to A2, which requires installing X square feet of acoustic paneling.
It's the tool for specifying and justifying complex acoustic engineering controls. Without this formula, specifying these controls is just expensive trial and error. The safety profession relies on these very specific logarithmic and algebraic tools to translate that invisible, cumulative hazard of sound into a measurable, guaranteed outcome for employee protection and, critically, for compliance.
We have just completed an extremely detailed, top-to-bottom exploration of the noise and hearing conservation program. We started with the delicate, non-regenerative biology of the inner ear, exploring how sensor and neural loss causes that irreversible high-frequency damage.
And we drilled down into the regulatory skeleton of the program. We defined that critical difference between the 85 dBA aption level and the 90 dBA PEL. We talked about the huge logistical and scientific necessity of that 14-hour quiet period before testing.
And most importantly, we dedicated a lot of time to breaking down the precise logarithmic mathematics that underpins this entire field. We saw how the nature of decibels necessitates these specialized tools, from LSAPAP to combined sound sources to the inverse square law for propagation.
And we showed how the TWA calculation converts the daily dose into an enforceable 8-hour average, incorporating that crucial 5 dB exchange rate. And then we looked at the engineering side, using formulas to quantify the effectiveness of expensive controls. The central lesson here, I think, is profound. The safety profession's ability to protect workers from this invisible hazard relies entirely on translating physical energy into precise, quantifiable risk using these mathematical tools. Mastery of these specific formulas is the difference between just a check-the-box program and effective, verified, lifetime employee protection.
That is the perfect connection back to the human element. And if we connect this all to the bigger picture, that 14-hour quiet period requirement, it highlights a fundamental real-world challenge. The safety professional has to assume the worker is recovering from all noise exposure in those 14 hours. But what happens if the worker's home life or their hobbies, their socioacoustic, are just as loud as their job? When you consider the precision that rule demands to filter out temporary shifts, it raises a really important question. Since noise exposure is a 24-hour reality, how much of the burden of noise reduction falls outside the workplace? And how effectively can a program that's focused only on the job site truly conserve a worker's hearing for a lifetime? Something to consider long after this deep dive ends.